Alrighty, welcome back, everybody. We were talking about light and electrons and all that fun sort of stuff. So we're going to do a few more just practice, just to get things going. But first, actually, let's do that. Let's start with that. Let's see if let's choose some elements. How about we do these guys? Give me the electron configuration for these four elements. And let's go ahead and use our noble gas shortcuts. So instead of writing out, 1s2, 2s2, 2p6, blah, 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 let's find kind of the noble gas before them and see if we can't use that as a shortcut. So just remember, if your element, like calcium or potassium here, is in period 4, we're going to want to use the noble gas from period 3, which I believe is argon. And then if your element is in period 3, like chlorine or sulfur is, you'll want to use the noble gas from period 2, which is neon, right? So let's go ahead and do these ones. So just to start, and as I said, this one will have neon. Hi, little one. What are you doing up here? You don't normally come up here. Little pirate. Okay, we've got our pirate friend here today to keep us company. Very nice, Lamonda. Yep. Looks good so far. I'm going to just move my neons over. I'm going to move this one over too. Just because these guys are going to need a little bit more space. Just a little bit. Right, chlorine's going to be 3s2, 3p5, right? Remember, we don't have a d orbital we're going to fill quite yet. Remember, we don't start filling 3D until after 4s, right? So after, for example, after calcium, once we get into the transition metals, that's when we start putting things into the D block. And then sulfur would be 3s2, 3p4, right? Cool. So hopefully none of this stuff is terribly confusing. Let's just take a moment to remember that argon is the same thing as neon 3s2, 3p6. So I'm going to leave that there. We'll come back to it later. We have a few more things to talk about in chapter 4. And then we'll kind of use this information as our segue into chapter 5. So with that being said, are there any questions so far on these like configurations or anything from the homework that's still like, you realized it at 11:30 last night when you were rushing to finish it on time? And anything like that, I'm happy to answer. Just also for a clarification on homework, if you have not turned it in, you still could turn it in late. You basically have up until I load the key. So I'll probably do that either today or tomorrow. So like if you're behind, you can still submit it. You'll get a few points off just for lateness, but as soon as I put the answer key up, I don't accept late homework anymore. Just because, it's too easy to just, copy everything I've done and be like, look, I did it. So remember, the homework is for you guys. It's a pain. Everyone hates homework. You hate it. I hate grading it. I hate finding it. We all hate it, but it's a very good practice for us. So it's, the best way for us to really learn this material. Okay, So let's take a look at an S orbital. These actually do have fun shapes. Well, maybe not so fun. But what these really are is, so previously, you had the nucleus in the middle and you kind of just drew rings around it and stuck some dots in there. Well, that kind of is it's a fairly good model of what things are actually looking like, but in the, later part of the 1900s, a lot of work was done in quantum chemistry, quantum physics, that actually had much more advanced mathematics going into them, and they were able to determine that some of the electron orbitals are like that. They're circular or spherical, if you want to think about them in 3D, and the s orbitals are indeed spherical. So that's kind of our usual one, right? However, it turns out that the p orbitals actually kind of look like little dumbbells. And they have in them what's called a node. And that's an area where you'll never find an electron there. And so it's very bizarre to us because the electrons in a p orbital essentially are just kind of traversing this entire shape. They're just going all around it at all times. And what these shapes are actually what's called probability distribution. So it's just, they're very likely to be found following this pattern. It's just a probability thing. However, the probability of finding an electrode at that node in the middle is effectively zero. And that's strange to us because the electrons can go from the top part to the bottom part and vice versa, but they can never cross that node. They'll never exist there. And so it's weird to us thinking, okay, how the heck do they actually travel from the top to the bottom without passing through the middle? And unfortunately for us, that kind of is normal physics. For us, if we wanted to go from the top to the bottom, we would have to walk through the middle, right? Assuming we could not leave that shape. However, electrons and things in the quantum realm do not need to obey that. So they can kind of seemingly magically reappear at the bottom if they're moving from the top to the bottom without actually crossing that node. It's very strange, does not make sense, but that is the world of quantum. It is not the same as classical physics. So everything you know about normal physics applies in the real world, but electrons don't necessarily follow all of those rules of physics. Alrighty, so I'm just showing you what these look like. You can go through d orbitals. D orbitals, actually, there's some interesting shapes going on. You're going to have kind of four-leaf clovers. And these guys are actually, you're going to have, you remember that there's three different p orbitals, right? They all look the same, they're just in different shapes, or different directions. So that's one of the p orbitals. You'll find another one that's horizontal instead of vertical, and there's kind of one that goes diagonally in just the x, y, and z directions. That's what the p orbitals look like. D orbitals are interesting. You'll have four of them that look like this four-leaf clover, and you'll have a fifth one, which is my favorite one. It's got the p orbital, but also this like kind of ring around the middle. And again, you've got that same idea here, where while that ring is not necessarily connected, I'm really a crappy drawer, artist, whatever you want to call it. But so that ring is not actually touching the orbital. But again, electrons can hop in and out without ever leaving, or crossing into the empty space. And then f orbitals are just completely strange. They look like little flowers, and they have all sorts of different ones. You have ones that look like this with two rings now. We're not going to worry about the shapes of f orbitals. You really don't even talk about them until very advanced chemistry. So, again, for us, f orbitals, just forget about them. F for forget. I'm not really going to ask you, questions on these, but I did want you to understand what these kind of look like. So it's just mathematical representations of what the probability of where the electrons are going around the nucleus. Okay, cool. So that out of the way, let's talk about some trends now. So we're going to have a couple of trends we're going to talk about. The first one we can talk about is size. And we're going to see that the periodic table, which is organized according to atomic number, right? And has also got things like sorted into groups that, actually, I guess we haven't really talked about this stuff. Before we go on to size, so periodic table. Here it is. Remember we had all those lovely blocks. We're going to see, remember we had all these columns in the periodic table. Those are what we call groups. And elements in the same group behave, let's see, I can't spell behave similarly. So that means, for example, here are some elements in our periodic table. We know that oxygen and sulfur are much more similar than, similar to each other than to nitrogen. Because oxygen and sulfur are in the same group, they are going to have similar chemical properties. And that means we're going to see that they will behave very similarly to each other in chemical reactions. And so even though nitrogen is right next to oxygen on the periodic table, oxygen is going to be much more related to sulfur in terms of chemical reactions than it is to nitrogen. And the same thing too if we put selenium on there. Again, oxygen and selenium are much more similar than oxygen is to nitrogen, or selenium is to nitrogen. Okay, so it's kind of the group that determines the properties of that particular element. And what we also notice is that all of these guys would have something that ends with p4 electrons, right? So oxygen, that would be 2p4, sulfur, that would be 3p4, selenium, 4p4, right? So they're in the same column. They're going to all have kind of a fourth electron in the p subshell. And that's going to be why these things are going to behave more similarly to each other than to something that has p3, for example, like nitrogen would, or phosphorus, or whatever. So that's kind of the reason that these things are going to be much more similar, because, I'll just write that out, they have the same number of valence electrons. And so we can see that all of those, so oxygen, sulfur, selenium, are all going to have 6 valence electrons, right? They're going to have something S2 and then something P4, right? Those are going to be their valence electrons. We remember that d electrons are never going to be valence, so it's always just S and P electrons that we're looking at. So all of these guys in that group are going to have something S2, something P4. All of those put together, that's 6 valence electrons. And so we're going to have some shortcuts here. We often number these groups. Let's see. Yes, I'll fit this. And then, of course, here's 3 through 10, which we don't care about in this class. Those are transition metals. We don't care. There's a fun thing that we can think about in order to figure out the valence electrons. You'll also see these sometimes as like 3A, 4A, etc. Instead of 13, 14, 15, 16, 17, 18. But it's just different periodic tables will display it that way. No difference. The groups, again, are still going to be the same. Notice that everything oh my goodness, everything in group 1 has 1 valence electron. Group 1, of course, would be like, lithium, sodium, potassium, hydrogen, etc. Oh, let's not even put hydrogen. Let's not worry about hydrogen right now. Rubidium. Yeah, rubidium's in there. All of these guys will have one valence electron, right? Let's just double check. We see we have potassium there. We scroll back up. We did potassium earlier. We saw that its valence was 4s1. 1 valence electron. Guess what? Everything in group 2 has 2 valence electrons. And that would be something like magnesium or calcium or beryllium or whatever. All those guys would have 2 valence electrons. And again, we saw that with our calcium earlier. Now, interestingly, when we go up to group 13 is when we have 3 valence electron. And guess what? If we go to 14, that's 4 valence electrons, 15 has 5, 16 has 6, 17 has 7, and 18 has 8. And instead of writing the same sentence a million times, hopefully you can see the pattern here. Right? If you just basically subtract 10 from the group number, that's how many valence electrons it has. Except for 1 and 2, those just have 1 and 2. So, easy way for us to find out. So, if I wanted to ask you, how about phosphorus? I could ask you how many valence electrons that has. You could, of course, come up with its electron configuration and count the electrons, but in the interest of time, it's a lot easier to just find which group potassium is in and just get it from this pattern that we have up here. And so if we look, we see phosphorus is in group 15, right? And so, by the way, I keep forgetting I have the periodic table. We see, notice at the very top of the screen here, we have the numbers 1 through 18. Those are our groups. We can see phosphorus is number 15, right? You can kind of see my circle hovering over it. We see that that's in group 15, which is going to tell us that phosphorus has 5 valence electrons. And so all you have to do to find out how many valence electrons something has is to just go ahead and find it on the periodic table, see which group it is, and that will give you the answer. Alrighty, we also have some fun names to learn. Group 1 is also known as alkali metals. Group 2 are what are called alkaline earth, if I could spell that correctly. So these are names that people refer to groups of elements as. So everything, sodium, potassium, lithium, all those are collectively referred to as alkali metals. Just a fun name they have. Alkali and alkaline typically refer to basic things, and we're going to see that when these are you're going to learn in Chem 111 that when these guys form oxides, these will tend to be basic oxides. And so that's where the name alkali or alkaline comes from. Skipping ahead, we don't really have names that we're going to need to know up until group 16, which is going to be known as chalcogens, which means they are chalk forming. We have group 17, which are called halogens. Those are salt forming. And then we have the illustrious group 18, which are our noble gases. So these 5 group names you will want to learn. It's often easier to just describe a particular. We can say, halogens behave this way. It's a little bit easier to do that than to say chlorine, fluorine, iodine, bromine, astatine all behave this way. It's just easier for us to say collectively halogens behave this way. Okay, so these ones you will want to know. So fun stuff there. Okay. Anything else? Yeah, let's talk about one last bit of the periodic table here. Periodic table, here it comes again. I should just have this saved so I can just copy and paste it. Okay, where is boron up here? Then we have silicon, etc. Okay, here we go. We're going to see that everything on the left side of the periodic table are all going to be metals. We'll talk about metals in a second, but for now, this is kind of where we're going to talk about them. It's going to be everything from this zigzag that I've drawn to the left, except, of course, hydrogen. Hydrogen is not a metal. Obviously, hydrogen is a gas, right? Our metals we don't typically think of as gases. Our pirate has come up again for another visit. Everything that's going to be on the right side are called non-metals. I don't know why I drew that arrow there. Let's get rid of that. Oh, not that one. Okay, yeah. Okay, so you're wondering what the heck, how about this squiggly line? Stuff along the squiggly line, those are going to be kind of in between. We call those metalloids or semi-metals. Either name, they're both kind of interchangeable. And that's going to include boron, silicon, and as we just, everything that's kind of touching that zigzag line as we go down will be considered, basically it's the stuff underneath that zigzag line. However, most of the elements we're going to be able to very clearly define as non-metals or metals. Okay, just so you know, hydrogen is a non-metal. Okay, if we think about hydrogen, it's a gas. Metals are not gases. We're going to see non-metals will be gases. Okay, so let's talk about metals and non-metals real quick. Then we'll talk about size and all that fun stuff. So, I want you guys to tell me some properties of metals. When you think of metal in your mind, what do you think of? How do you know something is a metal? Like, however, if I were to take this corkscrew, I see this part of it is made of metal. How can I tell? Physically. Just physical properties. How do I know this piece is metal? Yeah, shiny. That's a very good point right off the bat. I know we did this at the very end of Thursday, but remember that was kind of an optional day. Yeah, these are typically quite dense. Very often they are solid. What other things do we have? Very often also metals are silvery. There are a couple metals that are not, like for example gold or copper. Those are pretty much the only metals that are not silvery colored. Everything else is, platinum, silver, sodium, magnesium, they're all silver. Or gray, but shiny gray. Let's see, yeah, they're good heat conductors. We make our copper, we make our wiring out of copper. Because copper is a good conductor of electricity. We also know that we could make cookware out of copper, or iron or aluminum or whatever, because they also conduct heat very well. Interestingly to know, fun fact for you guys, the best conducting metal in existence is silver. However, obviously it's way too expensive to use silver wiring, even though it is a better conductor of electricity. So in very, very high-end things, you might have silver wiring, but for most purposes, copper is pretty close to silver's conductivity. So and it's way, way, way cheaper. So and does not corrode as well. Okay, cool. So let's see. Anything else I want to talk about with these guys? Not right now. Okay, so non-metals are typically going to be quite dull. They are not going to be shiny. We're going to see these are typically not dense. Many of these will be gases. There are two elements that are liquids at room temperature. That's mercury and bromine. Mercury is a metal and bromine is a non-metal. So I'm not going to necessarily put those on this list, just because we're kind of doing like most of these things. So most non-metals are gases. However, bromine is a liquid, iodine is a solid, phosphorus is a solid as well, but most of your non-metals will be gases. These are often colorful or colorless. So, for example, sulfur is bright yellow, phosphorus can be red or white, depending on the formation it's in. Chlorine is kind of greenish. Iodine is purple. Bromine is kind of reddish brown. These guys are often much more colorful just by themselves, whereas the metals are kind of silver colored. And these guys are also poor conductors. Okay, so knowing where our things are on the periodic table, I'm going to zip right back up to the top real quick, and then we'll come back to this list, okay? So I will come back. I just want to show us one thing real quick. So one big thing about Chapter 5 is we're going to see that all of these elements are going to want to become like noble gases, right? They all aspire to nobility. They all want to be noble gases. And we're going to see that there are several ways that things can become noble gases. One way is to either gain or lose electrons. And we're going to see that if we're looking at it, this calcium and potassium, we're going to see it's easy for them to lose electrons to become like noble gases. For example, potassium has just one valence electron. if it loses that 4s electron, it will have exactly the same configuration as argon does. And so we're going to see that chemically it's going to be pretty willing to lose that electron, because that'll get it to become like a noble gas in terms of its electrons. We see on the other side here, sulfur and chlorine are more likely to gain electrons. Yes, they could lose all of those valence electrons to become neon. However, it's going to be a lot closer for them to kind of go towards this direction instead. If they can gain electrons, they can mimic argon. If they were to lose electrons, a lot of electrons, they could mimic neon, but it's a lot easier for them to mimic argon. Okay, so that being said, we're going to see metals will tend to lose electrons in chemical reactions, and nonmetals will tend to gain electrons. And as a result, these ones will form positive ions, and these ones will form negative ions. Right, and we remember positive, we call those cations, and negative ones, we call those anions, right? So we're going to see that when metals and nonmetals come together, metals will tend to give away their electrons to the nonmetals, and we're going to end up having a positively charged metal and a negatively charged nonmetal. Okay, and we're going to see that starting tomorrow when we talk about naming and ions. We might get to that today, but we'll see. Cool. Any questions on this stuff so far? This is our happy list. Okay. So now let's talk about trends in the periodic table. Alrighty, here we go. So let's look at size. So let's compare a few atoms here. Let's compare nitrogen, oxygen, and fluorine. Let's see how many shells these have and how many protons these guys have. Let's just start with those two. I'll do our protons for us because why not? Oh, bad. Shame on me. 9 protons. Right. If we look at these particular elements, we're going to see all of them are in the second row of the periodic table, so they should all have 2 shells. And if we kind of go back to our simple atomic model, right, we have nucleus here, we have our rings around it. All of these guys are going to have 2 rings. And, oh gosh, why did I do this? Okay, cool. We're going to see that these guys kind of look similar, right? They all have 2 shells. They have different numbers of electrons and protons, sure. But keep in mind that, remember, we have, we talked about the atom kind of being like a baseball field, right? Where we had that grain of sand in the middle, and we had the whole stadium being the entire atom, right? So the electrons are, really far apart from each other, and they're kind of zipping around all over the place, right? We're going to see that fluorine, which has more protons, has a more positive nucleus, right? The more protons you have, the more positive your nucleus is. And we're going to see that that is going to, that'll basically bring the shells closer to the nucleus. And so we're going to see that the fluorine, having 9 protons, is going to bring in its shells a little bit closer. Just because, they're just more attracted to the positive nucleus. So the more positive the nucleus is, we're going to have kind of a shrinking of the atom, if that makes sense. The positive nucleus is going to bring in those negative electron orbitals, those electron shells that we have around this. And we're going to see by comparison, this is a less positive nucleus. And that means this doesn't pull in the shells as much. And so I've kind of drawn them here in this way. We're going to see that nitrogen is going to be bigger than oxygen, which is going to be bigger than fluorine. All right, does that kind of make sense? So our strongly charged positive nucleus brings in the electron shells. All right, they all have the same number of shells, so they all have kind of the rough, like, original structure. However, more protons is going to bring those shells a little bit more inward. And so we're going to see that as we go, let me write this in black. So left to right, atoms get smaller. So we're going to see that's going to be part of this trend. Okay, and I'm going to illustrate this in a bigger picture in just a second, but let's compare a couple more. And bromine, why not? So looking at these ones, again, I've kind of drawn them obviously, or I've tried to at least. We're going to see the more shells you have, that's going to lead to you being a bigger atom. All right, just the more shells you have, shells take up space, right? The bigger shells you have, the further they are from the nucleus. Even though bromine does have a lot of protons, we're going to see that it's going to drag in kind of the inner shells, but that outer shell is just going to be too big. It's going to be way out there, way out there. So the more shells you have, you're going to have a bigger atom. And hopefully that makes sense, right? Just, size-wise. And so as we see, as we go, up the periodic table, atoms get smaller. And so what that means for us here's fluorine. We're going to see, typically, by the way, for these trends that we're going to be talking about, we just ignore the noble gases. So we're not going to think about noble gases for any of these trends, so just kind of set them aside out of your mind. We're not even going to think about this particular, don't think about this column. Okay, that column doesn't exist for us. We're going to see that this guy will be the smallest, and francium way down here will be the biggest. Right? So francium is going to have the most shells, and that means it's going to be really big. And compared to everything else in its row, francium has the smallest number of protons, so it's going to have the least attractive force on those outer rings. So we're going to see that as we go up or to the right, things will get smaller. So as long as you remember where the biggest one is and where the smallest one is, you can kind of make some, judgments about whether an atom will be bigger or smaller than another one. So if we were to compare, let's say, let's compare these two. Which one of these is going to be the bigger atom? Let me draw them on for us here. Carbon is right here. Silicon is right there. Which one of these is going to be the smaller or bigger atom? I forget which one I said, but we'll be able to write either one. Which one's bigger? Yeah, carbon is going to be... Wait, no, carbon's not bigger. Remember that these lines are going to be our comparison here. So as we go up, we get smaller, right? So carbon being above silicon means carbon is going to be smaller. I'm sorry, I forgot what I said, Lamonda, also. You're both right then, in this case. So, yeah, because I forgot. So, this is what we'll do. This one will be bigger. This one will be smaller. Because, yeah, I'm sorry, Lamonda, but you're both right. I'm sorry, I just forgot which question I asked. So silicon's bigger, carbon is smaller. I think we're all on the same page there, hopefully. I just forgot which question I asked. But is this okay? Is this what you were trying to say? Okay, cool. In that case, let's do another comparison. Rubidium and magnesium. Okay, so let's find those on the periodic table. Rubidium is somewhere over there. Magnesium is up there. So which one of these is going to be bigger? This time I said bigger. Okay, I will remember. Which one of these guys is going to be bigger? Rubidium is going to be bigger, yes. Right? So, the closer you are to francium, the bigger you are. The closer you are to fluorine, the smaller you are. So that's going to be the trend here. So as long as we can figure out... I'm never going to ask you, by the way, for example, I'm never going to ask you to compare carbon and phosphorus. Right? Because that would not be a fair comparison, because one of them is up more, but the other one is to the right more. And so that one would not be a fair comparison to make. So I'm never going to ask you something like that. However, I could ask you, phosphorus versus silicon, for example. That would be okay. So everything that I would ask you, it would follow these trends. So in that case, let's do one more. Okay, so of these ones, of these four elements, which one has the smallest radius? So remember, if we imagine atoms are spherical, radius is related to how big it is, right? So small radius means small atom. This is just to put this more into the context of what a question might actually look like. So, for example, this could be a multiple choice question, right? Which of these has the smallest radius? So what we need to do is find them on the periodic table, right? So, my goodness. Okay. Let's see. So barium is somewhere here. Calcium is somewhere here. Sulfur, chlorine. Yeah, so indeed, of these four, we find them on the periodic table. We find the one that is closest to fluorine. Remember, fluorine, the smallest one. The closest to fluorine is going to be chlorine. Now let's use this one. We also see that that one is going to be the furthest to the right and the furthest up. And so this could be something that I could ask you on an exam. I could ask you to compare a couple of things and ask you which one's the smallest one, which is the biggest one, whatever, something like that. Okay? Okay. So that is the trend on size. All right, let's talk about one now called ionization energy. That is how much energy it takes to remove an electron from an atom. And so, here are my pretty pictures. Get ready for it. These are all his happy electrons he's sitting on. And here's another one. Okay, I hope the yellow is visible. I wanted them to be like coins because here comes a burglar. He is evil, and he is coming to steal electrons from these poor, unsuspecting people. And so, our burglar here has two options. He can steal from the, I guess not to say that. Okay, I should not have given him a gender, but whatever. It's a guy. He's coming to steal things. Okay, so he is here to steal the money. So he has two options, right? There are two victims that he could choose from. Let's say that both of these are, they have the same amount of money, let's say. And if we think about it, this one in his house has got his money kind of thrown all over the place, whereas the other one has all the money kind of kept in one spot and he's sitting right on top of it. We're going to think, okay, this little burglar is going to come up, he's going to take this one and run away. And by the time that our little victim on the left realizes it, there's no way he can kind of protect all of those electrons at once, right? So the burglar is going to just come in, take it, and go away. And so we're going to see that this is going to be somewhat like a large atom, which has a lot of electrons all over the place. And this one is going to be a small atom. We think about it kind of again related to that nucleus thing. The small atoms, remember the electrons are held really close to the nucleus? Whereas in the large atoms, things can be really, really far away from the nucleus. And as a result, it's going to be easier to steal an electron from a large atom. So if you think about it, like this guy's in this big old mansion, he can't watch all of his coins at once, so burglar just goes in and steals one. The other guy probably might even not notice. Whereas in the small atom, small house, all the coins are in the same spot. It's very easy to protect them. So it's going to be easier to remove from a large atom. Okay, because they're not tightly held by the nucleus. And that means that this is going to have a low ionization energy. Right? It's easy to take the electron, so it does not require a lot of energy to do. However, to try and take an electron from the small atom is going to require a lot of energy because those are held nice and tight, close to the nucleus. And so we're going to see, boom, here's our periodic table again. That, oh my goodness. Once again, fluorine and francium will be our marker elements. We're going to see that fluorine being the smallest, right? We have already established that. We'll also have the highest ionization energy. I'm just going to say IE for ionization energy. Francium being the largest will have the lowest ionization energy. So, as we go up and to the right, just like before, the ionization energy increases. So it's easy to steal from big old francium down there. Francium has got 7 shells, and those are really far away from the nucleus. Very easy for something to come in and just pluck that electron off from that very outer shell. However, fluorine being very close together, it's going to be very hard for something to take an electron away. No calculations, just comparisons. So lucky us. No math, just conceptual stuff. Yes, lucky us. This is our break from math. Actually, we're not going to have math again until... let's see. We got the polarity, then we got intermolecular forces, gases. This is chapter 7. Yeah, we're not going to have math again until chapter 7, so lucky you. Cool. So this will be the same thing. So if we take... which is easiest to take an electron from. Let's take those 4 same elements from before. Let's digest this question. Easy to take electrons. What does that mean? Does that mean low ionization energy or high ionization energy? This means low ionization energy. Exactly. So, looking at that, exactly, you guys are on top of it. Awesome. Awesome, awesome. We're going to see that barium is going to have the lowest ionization energy. So this is kind of the only way I can, trick you on these sorts of questions is just kind of worded in such a way. But that's it. So as long as you understand, these relationships, you can follow the trends. So understanding that low ionization energy is easy to take electrons from. Okay? And so the trend is just like before, fluorine is going to be the hardest one to steal from, and it's also the smallest one. So lucky us. Alrighty, last trend of the day is going to be metallic character. And guess what? We have, that's not right. We already have kind of done this. We know that the stuff on the left is metals, the stuff on the right is non-metals. Guess what? Guess what? This is going to be the least metallic, and francium will be the most metallic. So look at this. As long as you remember these two elements and the trends that they have, we'll be fine on all of these. So we're going to see that fluorine is the least metallic element. And that makes sense, right? It's smack dab in the middle of the nonmetals. And if we remember that nonmetals will want to gain electrons and metals want to lose electrons, we just described that francium, it's easy for it to lose electrons. And that makes sense. It wants to lose that electron. So it's going to say, yeah, please go right ahead, take it away. It's not going to take any energy whatsoever to get rid of this electron. And so it's exactly the same trend. So as you go up, you get, less metallic. And as you go to the right, you also get less metallic. Easy. So hopefully these trends today are a welcome break from all the electron stuff we've done so far in this chapter. These trends are typically not too difficult, so you'll just want to kind of practice with them. So one thing I want to point out before we end today, let me pull up our Discord real quick. Is it in here? Handouts, maybe? Yeah. Okay, so let me see. So Discord, is this the one? Yeah, okay. So go here to this handouts thing. There's this table I've uploaded called Summary of Ions. Tomorrow we are going to start working with this. So if you open it up, which I realize I'm going to have to now show an additional screen. Well, whatever. Open it up. On the second page, you're going to see this chart called polyatomic ions. You're going to want to start learning those. Okay, so start learning polyatomic ions, which are on the second page. Okay, and that means the charge and the names and the formulas and everything. Okay, so at some point you will want to, I mean, ideally commit this to memory. There are a lot of patterns here that you'll be able to see, but yeah, work on that. It'll make your life a lot easier. While I cannot force you to memorize it in the online environment, it will make things a lot faster for you if you do. Okay, with that, I'll see you guys tomorrow. We'll continue. We're going to start going into Chapter 5, which is about naming and molecules and fun stuff like that. So, yeah, see you guys tomorrow.